Morning to everyone. I'm Professor Cristina Bettin from Ben Gurion University of the Negev, but I'm president of the Association of Italian Scholars and Scientists in Israel, AISI. So it's my pleasure, my great pleasure, to welcome you today to these webinars organized by AISI in collaboration with the Embassy of Italy in Israel, in particular with the Embassy Scientific Office. We had hoped to launch this initiative much earlier, but the circumstances of recent months forced us to postpone it several times. We are therefore especially pleased to be here today and look forward to developing many more joint academic initiatives that will further strengthen scientific cooperation between Italy and Israel. So I'm very pleased to welcome now Professor Giuseppe Falini. Professor Falini is the scientific attaché of the Italian embassy here in Tel Aviv, who is representing the embassy on this occasion and will also serve as a chair today. Professor Falini is a professor of general and inorganic chemistry at the University of Bologna. His research focuses on biomineralization, biocrystallography, calcium carbonate formation, biorespiratory materials, and the sustainable valorization of marine biogenic waste. He has authored more than 280 peer-reviewed scientific publications and is co-inventor of 3 patents. Through his distinguished career, he has coordinated and contributed to major international research initiatives, including IRC, its Advanced Grant, the Graphene Flagship, and several Horizon Europe projects. So please, Giuseppe, the floor is yours.
Thanks. Can you hear me?
Yes.
So thanks so much, Christina, for the warm welcome. So I would like to share now my screen. So just a second, please. Okay, I hope now you can see in full screen. So First of all, I want to say to everyone, which is a great pleasure to chair this Italy-Israel scientific webinar on behalf of the Embassy of Italy in Israel. I'm also pleased to convey the greetings of the ambassador, who really appreciates this initiative. He stimulates this initiative, and he hopes that this initiative will be of great success. So doing this, I cannot also not thank the ISI, because this webinar comes thanks to them, to all the scientific coordination team of ISI, and I was also to thank the Bar-Ilan University, the Qedma, and all the speakers and participants who have contributed to the organization of this initiative. This webinar of today addressed the research field located at the intersection of fundamental physics, advanced computation, engineering, and technological innovation. So we are really in a multidisciplinary approach. And this is what is necessary in quantum technology, because quantum technology are becoming increasingly important platform for both scientific research and economical development. They offer new approach to studying physical systems, processing information, and addressing computational problems that may be extremely difficult to solve using classical methods alone. And we will learn about this today. Now, why this webinar? And we are timing with this webinar. Quantum technologies are progressively moving from what it was a few years ago, a scientific promise, toward the increasing advanced experimental platform. However, many important challenges still remain. And at the present day, quantum processors already provide scientific instruments, but there are still a lot of problems to solve. This is at least what I learned. And in this context, quantum simulation play a particularly important role to the transition through quantum technology. And when we discuss quantum simulation, this is the topics of where we are going today. The Ising model, which provide an especially suitable framework for discussion, as I hope the speaker will explain us very well. I found that there are three elements particularly relevant. Simulation, meaning the use of controllable quantum platform to explore complex model. Scalability, connecting algorithms, hardware, and error mitigation strategy. And what I think is even more important, talent. Through the training of researchers able to operate across physics, mathematics, computer science, and engineering. So this comes really in this multidisciplinary environment as the scientific excellence becomes even more effective because it has to connect institutions, laboratories, innovation ecosystem. And Italy and Israel have high complementary scientific and technological ecosystem. Italy has a long-standing tradition in theoretical physics, material science, photonics, high-performance computing. Israel combines excellent academic research with a particularly dynamic environment for deep tech entrepreneurs, rapid technology transfer, and interaction between university, startup, and industry, which is really one of the milestones of this country. So connecting this capability can generate new opportunity for joint research, innovation, and advanced scientific training. The role of scientific diplomacy, which is I always consider a free zone, is to facilitate this connection. Diplomacy does not replace science or determines results. It helps science to move, to travel, to create opportunity for research, to meet, to support the transformation of initial contact in structural and sustainable cooperation. And this is the spirit also of this webinar. I will go now to the, sorry, what's up? I'm too fast. So I move now to the program, which really reflect this interdisciplinary character. We will have Professor Alessandro Silva that will discuss Ising dynamics with particular attention to quantum quenches, correlation, and entanglement graph. Then we will have Professor Emanuele Dalla Torre from Bar-Ilan University will present a recent experiment on Ising model using quantum computer. We are also pleased to have Professor Giovanna Morigi from Saarland University. We will address driven and open leasing system. And finally, we have the approach from the startup, Matan Ben Dov, who will discuss quantum simulation beyond classical limits and the contribution of error mitigation software to obtain reliable results from quantum processor. So just an organization note to ensure a current and focused scientific exchange, the question and general discussion will take place at the end of the fourth presentation. Now, I think my time is almost over. It's my big pleasure to introduce the first speaker, Alessandro, Professor Alessandro Silva. Alessandro is full professor of condensed matter theory at the SISSA, which is the International School for Advanced Studies in Trieste, specializing in non-equilibrium quantum dynamics, cold atoms, which in these days could be quite relevant in Italy, and strongly correlated system. So, Alessandro, the floor is all yours.
Thank you very much. So, Emanuele, I have to share my screen now. Share. Can you see?
Yeah.
Okay, fantastic. So, Okay, so thanks, Giuseppe. Thank you very much, Cristina and Emanuele, for organizing this. It's always a pleasure to be virtually in Israel. So I'm going to tell you something about Ising dynamics. In particular, my seminar is quite introductory, so I'm essentially going to set the stage for others. And so the first question we have to ask ourselves is, why are we still studying the Ising model in 2026? Because the Ising model was actually invented by Lenz, not by Ising, in 1920s, so more than 100 years ago, in the context of the study of statistical mechanics of magnetic materials. And by now, it has been studied a lot in all its possible incarnations in the various geometries, quantum, classical, on networks, in various situations. So why the Ising model turns out to be always interesting and still interesting in 2026? And as it was mentioned by Giuseppe, the reason are quantum computers. As you all know, because it's in all the news nowadays, in the past 20 years, 25 years, quantum technologies have made a major leap forward, to the extent that I remember 20 years ago when I was working on the first prototypes of qubits, already making a single superconducting qubit was a major achievement. And nowadays, there are companies who sell quantum computers made of superconducting circuits or of ion traps or of optical circuits or of many other possible platforms that can make quantum mechanical sort of calculations. What is the problem of all these platforms? The problem is that we are still in the context of quantum technologies in the realm of so-called NISQ, noisy intermediate scale quantum systems, which means essentially that our systems are operating quantum mechanically, but we don't have the possibility to correct errors within the system, and therefore the system are intrinsically noisy, which means that in a sense you have to figure out some way to test them, to benchmark their operation, and to figure out how good they are in doing real calculations. And in this respect, since most of this research is done by physicists, the Ising model comes handy because it's a simple model. It has been studied a lot. It's written up in terms of spins, which are essentially qubits. And we know a lot about it. And this is what essentially generated a lot of, and probably Emanuele will talk about this later, but generated a lot of interesting works lately in the past 3-4 years. In particular, there was a simulation of a two-dimensional quantum Ising model with a quantum computer with 127 qubits by IBM. There is also a study of quantum Ising glasses, which are essentially Ising models with disorder, and which are very interesting, for example, for optimization problems. And these are studied with another type of quantum computers that are so-called annealers, which have a significantly larger number of qubits, 5,000 qubits in the D-wave machine, and so on and so forth. So from now on, I'm going to switch gears, and I'm not going to talk about quantum computers anymore. I'm just going to talk about the quantum Ising model and what are some interesting features of the physics of the quantum Ising model that we studied, let's say, in the past 10 years, that I think could be interesting to study also in the context of quantum computers. And in order to do so, let me introduce a sort of sophisticated version of a quantum Ising chain, quantum Ising model in one dimension. So as you probably all know, an Ising model in its quantum incarnation is made out of two ingredients. The first ingredient is a spin-spin interaction, longitudinal interaction, that is in the x direction in this case, with an interaction that could depend on space, Vij. Typically, we see the nearest neighbor version. So the two spins that interact are nearest neighbors on a one-dimensional lattice. And in order to make this model quantum, you add a transverse field that, since quantum mechanically this operator will not commute with sigma x, adds some spicy, interesting dynamics. Now, this model was studied a lot in the past, let's say, 15 years, in the context of ion traps, simply because it can be simulated analogically with ion trap experiments. This was done, for example, in the group of Chris Monroe in Maryland. And in that case, what you have is an interaction Vij that goes down that decays polynomially with space, with an exponent alpha that can vary freely between 0 and something greater than 2, something like 3. Now, the Ising interaction is so the opportunity to study the physics not only as a function of transverse field and of J, but also as a function of the power of the decay of these interactions is actually an interesting opportunity, because it gives you a chance to study the crossover or the phase transition between short-range type of models or dynamics, which is what happens when alpha turns out to be greater than 2, and long-range type of dynamics when alpha is smaller than 2. So from now on, we will study what is known as quench dynamics. What is quench dynamics? You imagine starting your dynamics from a given quantum mechanical state, let's call it psi, and then you turn on, could be the ground state, for example, of the quantum Ising chain when H is equal to 0, transverse field is equal to 0. And then you turn on the transverse field abruptly in time, and you see what happens as a function of time. This is something that was done, for example, in these calculations that were done by one of my postdocs a few years ago, actually 10 years ago. In using tensor networks, not using a quantum computer, using tensor network techniques that are numerical techniques. I mean, it's not important to know what they are at the moment. So what I'm showing you here is the dynamics of what is known as the order parameter. The order parameter of the Ising chain is the magnetization in the x direction as a function of time, as a function of the final transverse field of my quantum quench, and for different alphas. You see that for alpha equal to 1.5, you have essentially two situations. If the transverse field is smaller than J, then you have oscillations, but essentially a saturation to a finite value that stays finite as you increase the system size. If the transverse field is greater than J, you have oscillations, but eventually the asymptote of the order parameter is equal to 0. Similarly, or actually differently, we get a different picture when we make this quench dynamics for the exponent alpha greater than 2, as I promised. When the exponent is greater than 2, what you see is that for transverse field greater than J, you still have only one oscillation and eventually 0 asymptote. When the transverse field is smaller than J, as before, you go to a finite asymptotic value, but as you increase the system size, this asymptotic value tends continuously towards 0. So we can actually represent the difference of these two situations that I'm showing you here by plotting the asymptotic value of the magnetization as a function of the transverse field for the different values of the power law exponent alpha. And this is what is done here. So for alpha equal to 0, actually, we can solve the problem analytically. And what we would get is an order parameter that follows actually the time average of the order parameter, follows this dashed line here. So it's essentially a Curie mean fieldish Curie-Weiss transition at h final equal to j with an exponent that is not square root. There is a logarithmic correction, but never mind. Now, as you increase alpha, what you get is for alpha smaller than 2, you get a plot that as you increase system size seems to stabilize towards something that does have a phase transition. You see that, you see that the value of the magnetization here is increasing and here is decreasing. We cannot go to too large system sizes because of, well, we would need a quantum computer for that. But we can certainly infer from these figures that there might be a phase transition here. Something completely different happens for alpha equal to 3. In this case, all the figures tend to go down as we increase system size systematically. And the finite size scaling is consistent with a value, an asymptotic value of the magnetization that is essentially 0. So the bottom line of these simulations that were done in 2016 roughly is that there is a dynamical phase transition for alpha smaller than 2 as a function of transverse field of our quantum quench, and this dynamical phase transition disappears when the exponent is greater than 2. Why does this appear? Because for alpha greater than 2, you have a short-range interacting model, and for short-range interactions in one dimension, we know that if we inject a finite energy density in our system, which is what happens when we do a quantum quench, the system cannot sustain a finite order parameter. So essentially, the order parameter will always go to 0. And this is this is consistent with that observation. By the way, this is something that was observed also experimentally in the group of Chris Moore in this paper here cited. Let's now come to the second topic of this talk, which is entanglement. I can skip this figure, it's not important. Now, entanglement. What is entanglement? Well, for those of you who have seen at least a bit of quantum mechanics, entanglement is the crucial property of quantum systems that essentially is obtained whenever you combine two ingredients: the fact that quantum systems can live in a superposition and the fact that quantum systems can have correlations. Correlations plus superpositions lead to entanglement. Now, a way to characterize entanglement in a quantum system, for example, in our one-dimensional quantum system, could be the following. We take our one-dimensional system, we choose a subsystem of linear size L. Our system is in a pure state that is written up here. We call A this subsystem here and B whatever stays outside. We construct the reduced density matrix rho AB by tracing all degrees of freedom outside our system, and then we compute the von Neumann entropy of this reduced density matrix. If this was a thermal density matrix, we would just get the thermal entropy, which, as we all know, is an extensive quantity that will scale with the volume of the subsystem. So in this case, we have a subsystem of linear size L in one dimension. So volume law, which is essentially what you get for thermodynamic entropy, means entanglement entropy scaling like L. If instead you have a pure state that is either a ground state of a system or has some special properties, for example, also in the dynamics of systems with long-range interactions, you can get a similar result. You will get that the entanglement entropy will scale not with the length of the subsystem in one dimension, but will scale with the area. So the area for a d-dimensional system, the area scales like L to the power d minus 1. In one dimension, d is equal to 1, therefore L to the d minus 1 is L to the 0, which means that you can either have a constant or a logarithm. L to the 0 can be either a constant or a logarithm. And these are the two possibilities that you have for ground states of one-dimensional system, constant in the case of a gapful system, log in the case of a gapless system. And it turns out that for the dynamics, which, the dynamics of the entanglement entropy is not very interesting, to be honest. What you will get is that the entanglement entropy typically goes to scales asymptotically in the asymptotic state after a quench as a volume law for short range interaction, and for long range interaction will go like log of L after logarithmic growth. It's not, you can ask me, what is the entanglement entropy telling us about the physics of the system? Is giving you an indication of the strength of the entanglement between the subsystem and the rest of the system. A proper way to tell this would be that up to some transformations that are complicated to describe, it tells you essentially how many singlets are connecting the two systems with one spin that is sitting in L and the other spin that is sitting in one system spin that is sitting in A and the other system spin that is sitting in B. But now another quantity that I'm actually trying to advertise here, because nobody is talking about it in the context of quantum computers, that could be interesting to study, is actually the quantum Fisher information that gives you a different type of information on the system. It tells you something about multipartite entanglement. Now, what is multipartite entanglement? The entanglement entropy tells you how many degrees of freedom what is the strength of the entanglement between your subsystem and the rest of the universe. Multipartite entanglement answers a different question. You want to know, given the full state, how many degrees of freedom in your full state are irreducibly entangled. So cannot be extricated by doing some transformations. Now, this is, to make a long story short, this story how many degrees of freedom are irreducibly entangled can be inferred by computing a quantity that is called the Fisher information. I don't think I have enough time to tell you everything about the Fisher information, everything I wanted to tell you, but let me summarize it. So if you have a certain operator, a certain observable O like this one, forget about everything that is written here, I don't have time. You can introduce a quantity that is called Fisher information that is essentially 4 times the fluctuation of this observable on the pure state that you're considering. Now, second statement, if you optimize this Fisher information, so essentially the fluctuations, on a set of operators that are essentially linear combinations of your spins with all possible versors, unit versors in all possible directions, and you maximize this quantity over this set of operators, and you divide it by the number of degrees of freedom, if this quantity is greater than m, then this tells you that you have at least m plus 1 parties in your system that are n plus 1 degrees of freedom that are irreducibly entangled. Why this is so? You can understand it easily. Oops, what is this? By looking at this example here. Imagine that you have a pure state that is essentially a product state of spins in the x direction, and you compute the fluctuations of the magnetization in the z direction. Of course, these fluctuations are going to scale like n, like the number of degrees of freedom. Why? Because you have n independent degrees of freedom, so you have n times the fluctuation of each one of them. If instead you have a state in which all degrees of freedom are irreducibly entangled, like in a GHZ state, this Schrödinger cat state that is written up here, quite easy calculation tells you that the fluctuations of the magnetization will scale like n squared. So you see that if I divide this quantity by n, I will get that an indication of how many degrees of freedom. Here I will get 1, here I will get n, and I get an indication of how many degrees of freedom are essentially irreducibly entangled in our system. This is something that is actually very important in the context of metrology. And now to finish, let me tell you something that I think is interesting. If you now take a system and imagine making a quench, for example, in our system for alpha smaller than 2, which had a dynamical phase transition. Now, dynamical phase transition, if you make a quench as a function of transverse field, you're essentially injecting a finite energy density in your system. So it's like as if you are essentially raising an effective temperature. And as you raise an effective temperature, you might hit a sort of analog of a thermal phase transition in your quantum system. For this thermal phase transition, if you compute, it's a thermal phase transition, but in a pure state, because the state of the system is pure. If you compute the multipartite entanglement close to this thermal phase transition, you will see that it scales like n, the subsystem size, to the power gamma divided by mu d, where gamma and mu are the critical exponents of the classical or the thermal phase transition we are dealing with. And this is the dimensionality. So the bottom line of this story is that by studying multipartite entanglement, you could, which is essentially equivalent to study the fluctuations of certain set of observables, you can get informations that are sort of complementary to the information you get from the entanglement entropy. In particular, in this case, all the states at finite temperature have entanglement entropy that scales with volume. So it's boring, the entanglement entropy in this system. Only when you study multipartite entanglement, you see something interesting. So, and this said, I'm sorry that for those of you who are not physicists, that my seminar was not properly tuned to be, to be for everybody. But I hope at least I conveyed a message that this model that was invented 100 years ago in a completely different context is still very interesting to test the physics, not only to test the physics of quantum computers and their operation, but also to discover some new interesting properties of quantum states. And this said, I thank you for your attention.
Thanks so much, Alessandro. I really appreciate you brought me back to my class of physical chemistry 35 years ago. So thanks so much. And now it's time to go to the next speaker. As I said, we'll have a question at the end of this, all the 4 presentations. So the next is my great honor to introduce my next speaker, which is Emanuele Dalla Torre. Emanuele is a full professor of physics at Bar-Ilan University. And his research focuses on non-equilibrium quantum many-body system, condensed matter physics, quantum optics, and ultra-cold atoms. So we move from cold to ultra-cold atoms. And his recent work includes quantum simulation on real quantum hardware and theoretical studies of Ising model dynamics and error-mitigated quantum computing experiments. So the talk that Emanuele will give us today is a recent experiment on Ising models using quantum computer. Emanuele, the floor is yours, and thanks so much.
Thanks Giuseppe for the introduction, and thanks Alessandro for your talk. Thanks everyone for joining. So this is of course an Italy-Israel event, but we have also special guests from Germany and from India, and maybe also other countries that I cannot recognize. And Alessandro, don't worry. I think that everyone who was not an expert already left, and we, everyone who is still with us, they are all, quantum physicists that can understand all your, maybe except from Christina. But Christina, she anyway understands. Don't worry. So great.
Thank you.
So this is Bar-Ilan University that is located not far from Tel Aviv. Well, this is a map of Israel. And Rehovot is where Weizmann Institute is located, and that Alessandro knows well as he graduated from Weizmann Institute in Rehovot. So, well, the scale here is 20 kilometers. So, I mean, everything is very close, and I really invite you to come and visit us. Yeah, so I would like to give a short introduction about quantum computing on the cloud in general, and then I will tell you a little bit about how the Ising model is relevant to this world. So in fact, quantum computing was born not 100 years ago, but only 10 years ago, so it's much younger. And it really started in 2016 with a beautiful show, experiment or demonstration by IBM, where they allowed anyone who wanted to just come and connect to their own quantum computer. At that time, their quantum computer, which was one of the most powerful ones on Earth, had just 5 qubits and the fidelity of 95%. So maybe 95 looks like a large number, but it means that every time that you try to apply a single operation on the quantum computer, you get a 5% error. So this basically automatically means that when you've done, I don't know, maybe 10 simple operations, you've lost your fidelity. So I mean, the fact that 95 is so far from 100 is really very problematic. Now, as you can see here, this is a part of a big table, and the big table includes locations, so like Americas, Europe, Asia, and also technologies. So there are many ways to build a quantum computer. IBM and many others chose one, which is called superconducting quantum computing, but there are other competitors as well, like silicons, envy centers, trapped ions, cold atoms, and photonics. And now, 10 years after 2016, I mean, today, we have this table which is much more populated. So there are many more companies that now offer to connect to their quantum computers, whether it is superconducting, trapped ions, or cold atoms. And the numbers are up. So if we focus on the example of IBM, for instance, you will see that IBM now has more than 100 qubits. Maybe this number is already, even not up to date, and the fidelities are much closer to 100%. So typically we speak of 99.8% per 2 qubit gate, which means that the error per gate is 0.2%, which means that roughly you can now apply hundreds of gates before your signal is known. So you have more qubits and more possibilities to explore. So the question now is, well, okay, I have access to a quantum computer, say 100 qubits. What's next? I mean, what can I do with such a quantum computer? So you can ask ChatGPT and it will give you an answer, but then you don't know if the answer is correct or not. So instead, I suggest you to come and ask us. So we have a center, it's called Kernel, which stands for Quantum Exploration and Research of Noisy Large-Scale Computing. In short, it means that we are the guys in Israel that explore quantum computers, near-term quantum computers, and ask this question: what can we do today? Before we'll get a futuristic quantum computer with 1 million qubits, which will arrive in the future. Now, what can we do? And so we set this center, which is actually a collaboration between 22 PIs and 6 different universities. Here you see the names of the PIs. And this event is part of our activities. We'll have also an in-person conference that you also see Sabine. So Sabine is also connected here. So, I mean, it's a really nice network, and many of the participants are also here at this event. So what can you do with a quantum computer? I think that, first of all, you should divide or make a distinction between classical application and quantum application. So if you have a real quantum computer, you can use it either to solve a classical problem, for instance, breaking the cryptography, like breaking RSA, or solving optimization problems. These are very interesting classical applications. But today I would like to focus on quantum applications. So quantum applications means that what you're trying to establish is a quantum simulator. So think of a real quantum problem, let's say a material. Okay, this would be graphene, or some other complicated real material, which is of course a quantum material, or a molecule. a complex molecule, a big molecule. And as you know, molecules are governed by chemistry. And as Giuseppe can teach us better, chemistry is quantum, right? So it's a quantum problem. So you really have a physics problem or a chemistry problem, which is a quantum problem. How do you solve it? The problem, so this problem, trying to solve it classically is really, really hard. And the reason is that in order to represent a quantum problem on a classical setup, on a classical computer, requires a huge amount of classical data, 2 to the n. So for, let's say, if you have only 30 qubits, like 30 electrons in your material, which is already a tiny molecule, a tiny material, you already would need a gigabyte of classical memory to store the information about that quantum state. So sure, you can do it. You can use a supercomputer and you will get, I mean, okay, 30, maybe it's, it's not 2, right? But it's still small. So using supercomputers is one way. Using analytical approximations in another, right? So you say, well, forget about the exact solution of the problem. Let's try to approximate it. Of course, you can combine both, right? You can do a numerical, classical computer numerical approximation. So you can have something that still runs on a quantum computer and also makes an approximation. So this is the best of your world. And indeed, it will allow you to get to, you maybe increase this number, maybe go beyond 30. But still, it's very limited and inexact. And the first one who pointed out this challenge is really Richard Feynman, who in 1981 already said that if you try to solve a quantum problem on a classical system, you get into troubles. And then the idea was, well, then let's use a quantum computer or a quantum system. And this was really pioneered in the world of ultra-cold atoms, where they explored simulation of electrons using neutral atoms. And now we try to do the same using superconducting circuits and all the quantum platforms that I mentioned before. Great. So, yeah, so quantum simulations using quantum computers is a field of its own. I mean, there are now, I think, probably hundreds of papers written on the topic. Maybe, I mean, if you include also theory, thousands of papers, but at least, tens or maybe hundreds of quantum implementations. In our group, we wrote 10 papers. So probably worldwide, there are definitely thousands of them. I just want to mention a few of them, which are, beautiful, like the idea of a time crystal, which is a presumably new phase of matter that was realized in a quantum computer by Google. Google are very good in PR. They also realized something that is related to a black hole. It's called the quantum wormhole. By the way, it turns out this paper was wrong, but anyway, it got to the news and people say, wow, this is a wormhole, maybe it's a black hole, maybe it will explode, our whole universe, because the black hole will destroy the universe. But no, actually, don't worry. This is not a real black hole, not a real wormhole. It's just a simulation of a wormhole, a simulation of a black hole. So it will not destroy our universe, which is already great news. People can realize, beautiful topological Floquet phases of matter. Here is just one example. There are many more. Really, this quantum simulation using quantum computers to simulate interesting physical effects is really an amazing topic. This is a very recent paper about chaos. Actually, Alessandro mentioned, I think, eternalization and chaos, and this is a beautiful, demonstration of quantum chaos in a quantum computer. But here today, I chose to select only one, actually two, just two examples related to the Ising model. So Alessandro mentioned a work by IBM in which they realized the dynamics of the Ising model. The problem with that paper is that later on people understood that actually one could simulate the same dynamics using a classical computer. So at the beginning, when the paper was published, this was not appreciated, but then other theory groups, improved the numerics and demonstrated that yes, by doing, all sorts of tricks, one can obtain the same result that were obtained on a quantum computing using a classical computers. Instead, the work here, it's a collaboration by TUM and Quantinum, and Caltech. So this is not an experiment on superconducting qubits, it's an experiment on trapped ions, and I think currently trapped ions hold the record in terms of the number of qubits that you can have and the fidelity. So the combination of the number of qubits and fidelities for the moment seems to be favorable for trapped ions, although of course people can also, there are also other opinions in the community. What they realized is the same model that Alessandro was showing you So the notation is a little bit different. Instead of sigmas, we use Z. Instead of sigma Z and sigma X, we use Z and X because, well, then we do quantum computing, right? So it's the same, it's just a different notation. But you have this Ising coupling and the transverse field. These are the two ingredients. And now comes a very important point, and one needs always to remember when doing a simulation on a quantum computer, which is that quantum computers are tunable, and they can create specific gates, but they can create specific gates one by one. So in the transverse field Ising model, you have two terms. You have an Ising term, the coupling, and you have a transverse field. And in the material, in a real material, you have both at the same time, right? At the same time, you apply a magnetic field and the spins interact one with each other. So the two come together. But in a quantum computer, this is not possible. What you can do, you can either make the spin interact or apply something equivalent to a transverse field. So the difference is that this is the interaction is a 2-qubit gate, right? So the interaction, the ZZ gate is represented here by blue. Okay, in this line, what you see, the horizontal plot is the time. And what you see is that you first apply, and the lines are the qubits. So there are maybe here 9 qubits. What you see is that you first apply a single qubit gate. So these green balls are gates that are applied on a single qubit gate, and then you apply 2-qubit gates. Now, because each qubit has 4 neighbors, so this is a two-dimensional lattice, square lattice. So each atom has 4 neighbors, right? Up, down, left, right. So what you need to do, if you focus on this qubit, you need to apply interaction with the upper, lower, left, and right qubit. So each cycle has 5 ingredients: a single qubit gates, and then this link, up, low, left, right links. And of course, what you can do, you can apply links. So you can apply the same gate on 2 qubits that are not connected. So you can apply at the same time this link and this link, but you cannot apply this link and that link. Okay, hope this is clear enough. But this is called discretization or digitalization or trotterization. These are all the same names for the same. What it means that you cannot apply at the same time the 2 ingredients. You first need to apply one ingredient and then the other. Now, if you do it very, very, very fast, then sort of the quantum computer maybe doesn't see the difference, right? Like in a movie. In a movie, you know that when you're watching a movie, it actually is just a series of pictures. But if you see the pictures very fast, you have the impression of someone moving your hand, right? It looks as if someone is moving. In reality, you just have tuck, 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 right? One after the other. So this is the same in a quantum computer because you cannot make the movie. So instead of having the movie, you have like discrete images. In this experiment, they were able to run up to 7 times 8, so 56 qubits, and apply 20 steps, which is equivalent for 4,000 gates. To get to those numbers, they had to implement something called the error mitigation. So well, we don't have time for that, but if you want to apply a lot of gates, you also need to apply a lot of tricks. And actually, Matan is going to speak about mitigation later on. So maybe he will speak about this experiment or a similar one. What was beautiful about this experiment is that they actually not only reported the quantum experiment, but they also performed really I would say, state-of-the-art numerics to make sure that no one is able to reproduce the results, at least not very quickly. So this is an example of the result. We don't really have the time to go over all the details. I just want to say that, first of all, well, this is an observable Z total square. So it's similar to the graph that Alessandro was showing. It's not really the local magnetization, it's the total magnetization square expectation value. The x-axis is time, and you have the two plots, one on the left and one on the right. And so there are two, in each of these plots, you see that there are dots. So the dots are the quantum experiment, and lines. And lines are the numerics. And what you see is that on the left plot, focus on the purple, which is the best possible result. So the best possible result which is the purple of the experiment, the dots, and the theory, the line, sort of match. So that's good news. I mean, the quantum computer and the theory works together nicely, so which is great. So this is like an easy scenario. The hard scenario, the quantum computer still works. So you see that these purple dots give something which looks okay. I mean, seems okay. I don't know if it is okay or not because, well, we don't have a way to check it, but it looks okay. While the line, you see that it starts okay. I mean, the line, which is the theory for the numerics, follows the experiment, but then at some point it goes well, it goes wild. Even at some point it will become negative, which is cannot be negative. And this is telling you that the numerics just breaks down. So at the beginning, both the experiment and numerics are okay, but then at some point the experiment still goes on for some time, and the numerics is lost. So this is an example of something where of a realization, one of the first realizations, maybe the first realization in which a quantum computer can solve a physical model, so not just a random circuit, a physical model better than the best available numerics. So we have still 2 minutes? No, 1 minute. So in 1 minute, I want to show you something about our own work. This is what we are doing here. We are actually just simulating for the moment. We haven't run it on the quantum computer yet. The dynamics of the same model, the Ising model. And what is special is that we apply a spin flip in the center. So the y-axis is the spin. So you have many, many, many spins. Okay, they all point down, up, but there is one spin that is pointing down on purpose. And then you let it evolve. And this spin that points down makes a lot of noise, makes a lot of confusion. You say this light cone, so it's sort of perturbing the spins around it. And this is the typical shape of a light cone. And what happens if you cut it? So if you cut, you will see that at the beginning you see nothing, right? I come from the left. Oh, I didn't know. Well, sorry, I didn't hear about it. I didn't know that there was a spin that flipped. Then at some point the news comes, and whoa, there is like a lot of new, or noise, because news came that there was a spin that was, making a revolt. So then all the spin starts to make a revolt, but then, as time goes on, the revolt goes down, and the oscillations, they are damped. But the question we asked, what was the shape of these oscillations? It turns out that there is a generic theory called the catastrophe theory that tells us that at least in the weak coupling limit, this curve must be an airy function, and indeed it is an airy function, don't worry. But the problem is that the catastrophe theory is a non-interacting theory, so it doesn't know anything about many-body quantum systems. And we asked what happens to many-body quantum systems, and the answer is that, of course, it's not an airy function, because it changes, right? Something needs to change, so it's not an airy function. But still, you see that the airy function has this 1/3 exponent, and the 1/3 exponent is the one that survives until the phase transition. So you see that when you change the parameter, this exponent remains 1/3 up to the quantum phase transition, and then at the quantum phase transition, actually the oscillations change their nature, or the exponent changes from 1/3 to another value. So, well, I hope you found it interesting, and if you find this whole meeting interesting, you are welcome to check out this event in person, which will take place on February 14th to 18th. On quantum simulations in Israel. We have still a lot of slots for students, and maybe also for some speakers. So check out kernel.org events. I'll put it in the chat, and my talk is over. Thanks.
Thanks a lot, Emanuele, for your really inspiring talk. I really appreciate. We will have combat at the end. Now it's time for me to introduce Professor Giovanna Morigi, which is a professor of theoretical physical chemistry. Theoretical physics. I have some bias in chemistry. Theoretical physics at the Saarland University in Germany, working on the interface of quantum optics, ultra-cold atoms, trapped ions, and open quantum many-body systems. Her research includes driven and dissipate quantum dynamics, structural phases of ion crystals, and theoretical approach to controlling complex quantum systems. Today, Giovanna will talk us about on the address-driven and open Ising system. Giovanna, the floor is yours. It is my honor to know you even in 2D.
So thanks for the very kind introduction. Thank you for the honor to be here and to talk. I would like to thank everybody, the people I see that I know, and the people that I meet for the first time. So I will start now. I share my slides. I hope that this is working again. And yes, so I changed the title a bit. I hope you forgive me. I would like first to tell you where I am, because when people hear about Saarland, Saarland is here in Germany, you see. It's smaller than Valle d'Aosta, okay? But there are 6 million inhabitants, so there is a high density of population. We have been recently granted 53 million from the Saarland federal government for establishing a interdisciplinary center, and the name of this center is CUTE, okay? Quantum technology. It brings together physics, computer science, mathematics, and engineering. There are now 8 professor positions that are being filled on the top of the group that are already here. And there are going to be soon announcement for position for junior group leaders or in quantum technologies and ranging on these subjects. So you see, I'm in Germany and I would like to motivate my connections now to Italy and to Israel. So I form a sort of triangle. I'm an Italian. In Germany, I've been working on ion Coulomb crystals and with friends also of Israel. Among them, there was also Shmuel Fishman. And we wrote recently a review that is going to be published. And this is about also how to design Ising models. And I would like now to focus on a work that is, I thought, shaped for this short presentation on the coherence cancellation in open quantum system. It is a work collaboration with Trieste, and the first author is actually a fantastic student of Alessandro Silva at SISSA, and this was his master. And I would like to go back to this picture that is very suggestive. It is a picture of an IBM quantum computer. It promises the quantum revolution 2.0, where now quantum technology are going to be disruptive in the everyday life type of uses, even in our data era. And I would like also to show now a plot that McKinsey made something like at the beginning of this decade, making a projection of when we expect to cover the full range from the basics to the daily applications. And what you see here are the time and the maturity, and there are 2 leaps. One has occurred at the beginning of 2020, from the control of quantum dynamics of small systems to the first prototype quantum computers. And this is what we call the NISQ era. Both Alessandro Silva and Emanuele Dalla Torre talked about it. And now we expect a leap in our possibility to create large systems that we control that would lead to the full value creation of universal quantum. And within this projection, now I highlight this region in time, in space and time, in which we find ourselves, where we deal with noise. And this is a noise intermediate scale, where also Emanuele Dalla Torre was showing what are the possible applications that one can exploit and is using the full-fledged of applications that are available. Now, when we deal in the NISQ era with quantum computing, we deal with noise. And what we want to do is to try to reduce any stochastic effect that doesn't match the dynamics that we target. We do it by means of trying to isolate the system, by means of what are called error mitigation type of protocols. And we want to go beyond that. We want to apply the full-fledged error corrections, but this will need the leap that you see here between 2 and 3, the phase in time. Now, if you look at the projection of McKinsey is end of this decade. But if we look at the present status, there is a certain, skepticism whether between 2030 we can reach this full control. And the NISQ era has been extended by several colleagues to at least another decade. And what I'm going to discuss is this leap is something that is based on an idea of reaching an ideal dynamics according to something we prefigured. And I would like to discuss how far this constraint is perhaps not too strict and whether it cannot be relaxed and change this perspective and perhaps get a crossover in the NISQ era towards the universal quantum computing. And by this means, I'm going to put forward the idea of needing alternative strategies beyond error corrections, and I will give some examples. The first point is that noise is a physical process. And as a physical process, we model it as theoretician, but we can also well understand in terms of, say, this quantum object being interacting with an environment. And the errors are all the physical dynamics we do not control, that we can describe as interaction with something else that is this environment in which we are embedded. And there is a very simple example for people working with atoms and MV centers, and the system that Emanuele Dalla Torre was showing. So this is a two-level system corresponding to the excited state of a bound electron in an atom. You see, I describe here the excitation in terms of this ball that occupies this higher level. This is the dynamics, and what we know is that this two-level atom, this dipole, will irreversibly emit radiation and undergo a transition to the ground state. And this occurs by means of emission of a photon in one of the modes of the electromagnetic field. These errors are the possible propagation that the photon can have. Detectors will detect this photon in terms of a click. What you see here is a plot of the statistic, the probability of a click as a function of time when the experiment is started. These bars are the number of clicks. For a sufficiently large number, one can fit this with an exponential decay. So here it's in logarithmic scale, so we see it linearly. Now, as theoretician, when we model these dynamics, we use what is called a spin boson model, where the two-level system is coupled with the bosonic modes of the electromagnetic field. These are harmonic oscillators. So this is the Hamiltonian of the spin. This is the Hamiltonian of the electromagnetic field. This is the coupling. And by means of this, we have a full control of full predictions of these dynamics in terms of statistics, of the clicks at the detectors, for the expert by means of the unraveling of these dynamics in terms of quantum trajectories of the spin, and in terms of the probability, which are obtained by means of the master equation. So we have full control on what this quantum model can tell. And now the point I want to say is, we have used it so far just for predictions. We have used it so far just for mitigation. Can we use it as a tool for designing the quantum dynamics of the spins, of this cube? And now let me go back to what I said before. Before I said, what are the strategies that we use in order to achieve universal quantum computing? What we would like to do? Well, we have this coupling because the electromagnetic field is always there, but we would like to cancel it. We would like to do anything so that it disappears. And we use lasers, oscillation, any type of classical control on top. And I would like now to use quantum interference and quantum superposition with the bath in order to achieve a target dynamics. I take an example. This is called the dephasing reservoir. So say, what does a dephasing reservoir does? You see here, this sigma z is the element that tells me that what are the eigenenergies of the Hamiltonian. Spin +1 is a state with a higher energy, spin -1 is a state with a lower energy. You see, if I have an interaction of this sort with an external environment, this will not redistribute population, but what it will do, it will destroy an optical coherence. So if I have a quantum superposition between excited and ground state, like I show it here, as a function of time, it will be destroyed. This is called decoherence. It's a loss of quantum coherence. It is essential, for instance, for metrology. Metrology, there is an important state. This is a known state. I write in these ways. For our purposes, we can assume these are two states of a superposition that is especially important if we are able to keep the quantum coherence between the two. Whenever we're able to write the state in terms of this vector state with a very well-defined phase between these two ket states. And this is particularly important because we can reach precision that is predicted by the Heisenberg limit, and if we can use the Fisher information of that Alessandro Silva was discussing before, we can quantify the capability, the resources that this type of state provides. But the point is, being so resourceful is also extremely fragile against the coupling to an environment. So as a function of time, the environment destroyed this phase information that is so resourceful for the metrology type of applications. So if I now do it, I can show this type of state in terms of this schema I was showing before as a superposition with the upper and the lower state of a ladder, of a spin ladder. And now the coherence, a coupling with the system with an environment will destroy this coherence, and this we will see it in terms of a fidelity that as a function of time will decrease towards 50%, and this 50% equal to 1 means I have a full quantum superposition, and equal to 1/2 it means that I lost this coherence information. Now I go back to the model, and in terms of the model I show here the coupling with the environment that dephases. I can cast it in terms now of this ladder spin that I call JS of Z, and now this interaction with the operator that is acting on the degrees of freedom of the environment, we say this operator XD. Now I am proposing as a strategy, we have been proposing as a strategy to use this full interaction, not in order to cancel it by means of broad strategies like the coherence-free subspaces or dynamical decoupling, but instead to take another quantum system. This other quantum system couples to the system, couples to the environment. The three of them undergo a full quantum dynamics, and because of this, we achieve a interference, quantum interference between the degrees of freedom of these three players that perfectly protect the null state. And as a function of this overall dynamics, the fidelity, you see, oscillate between 1 and 0.95. I would like now to provide the ingredients. These are for the experts. So the idea is to add a further Hilbert space, further degrees of freedom. What you see here now, there is the coupling I was showing before between this ladder operator and the degrees of freedom of the operator acting on the degrees of freedom of the environment. Then there is the interaction of this auxiliary system with the environment. You see it here. And on top, there is a correlated noise that gives that the interaction between system and environment is also correlated with the interaction with the ancillary system. This is, for expert, what are called spatially correlated type of environment. I'm not saying anything. See, on the time correlation, I'm talking about spatial correlation. And now the second ingredient we need is the possibility, say, to prepare this auxiliary system in a pure state. It doesn't have to be entanglement. It has to be pure. Actually, it doesn't even have to be pure, but for the simplicity of the presentation, I will take the pure state, say an eigenstate of a angular momentum operator. And now you see that if I prepare the initial state of the system with the null state, this specific state of the auxiliary system, and any state of the bus, I'm going to have, when I apply this interaction to this state, an interference between the part of the bus that acts on the system and the part of the bus that acts jointly on system and on C. Now, this term here can be designed in such a way to give to an exact cancellation of these two terms. And this is how, by means of adding additional degrees of freedom, adding an additional quantum system, adding quantum interference with the environment, we may achieve protecting a quantum state. Now, there is a room for optimization. This shows you that we can tune the coupling with the environment in such a way to go from a fidelity which is extremely not advantageous to the case in which the state is like it were perfectly isolated. And remember, we're isolated by coupling it to a further system. And now we can tune the strength of this coupling, or we can tune also the temperature of the auxiliary system. I didn't discuss it yet, in such a way to optimize the fidelity at steady state. And this is valid and work for any type of power spectrum of the environment, so also for what is called 1 over F noise. And here I want to emphasize, we don't have any error correction strategies for 1 over F noise, but this way would provide a way to protect the system, at least for certain dynamics and states. I am finished. I would like just to give a summary. And in the summary, I'm telling you that I did discuss correlation between system and another quantum system can protect the system. So adding further interactions. I didn't discuss, but we have been looking at how to couple the system to an environment and speed up the propagation of information within the system, which is essential also for the case of the quantum wormhole or quantum chaos that Emanuele Dalla Torre was discussing in the example of the work of Google. And I didn't discuss how other type of non-unitary dynamics like monitoring and feedback can change the time complexity of a quantum algorithm, like a quantum search. This time complexity tells you whether this algorithm is going to converge on a time that permits you to overcome the complexity and the time scales of classical computer. And in a quantum system, we showed that for NIST devices, measurement and feedback can provide a definite advantage. And with this, I would like to put the message that the next step of these insights that we have been getting is what we want to do is to design optimal non-unitary quantum dynamics, taking into account the degrees of freedom of the environment and of possible auxiliary systems. So I finish by thanking several people, and in particular the people that have been contributing to the work, have been leading the work I was showing, Fabio Manselmi and Fabio Benatti from the University of Trieste, and Giuseppe Daurea at SISSA, and I show here a picture of the group in Saarbrücken on the day of the kickoff of our Quantum Technology Center. I thank you for your attention.
Thanks a lot, Giovanna, for your very interesting presentation. We all appreciate. And now we go to the next speaker will be Matan Ben Dov, that has recently obtained his PhD in physics under the supervision of Emanuele Dalla Torre, and is now a quantum computer researcher at Qedma, working on methods for improving the performance of near-term quantum computers. His research also includes quantum state preparation, circuit optimization, tensor network methods, and error mitigation technique for running useful quantum simulation beyond the classical limits. So Matan is going to discuss quantum simulation beyond classical limits and the contribution of error mitigation software to obtain reliable results from current quantum processors. So, Matan, the floor is all yours. Thank you.
Thank you very much. I have a bit of a technical difficulty. Let's see if I can share my screen. Okay, do you see it? Is this my screen? Okay, so it works.
Yeah, we can see you.
Thank you.
Thank you.
Thank you. Okay, so thanks everyone. My name is Matan. I'm a quantum researcher at Qedma. We are an Israeli startup company of quantum algorithms, and we're focusing on error mitigation, error reduction solutions for currently available quantum hardware. And in this forum, I would like to present one of our newest works about quantum simulation experiments beyond classical limits using Qedma's error mitigation software. This simulations will start the transversal Ising model as was presented here by Emanuele, Alessandro. So thank for the very, very nice introduction. So I'll be able to go a bit faster and hopefully everyone will be with me. So what defines in general algorithmic quantum advantage, right? In the industry, that's one of the goals that we are all trying to reach, is some demonstration of algorithmic quantum advantage in which quantum computer performs better than classical. So in which way do we quantify the word better? So we can either talk about a faster solution of the problem. So quantum computer outputs the right solution much faster than classical hardware. We can talk about maybe cheaper solutions. So there is a price for access for CPUs and GPUs and clusters, and there is a price for access to quantum hardware and QPU time and having QPU time. So ideally, quantum advantage also will improve in that front. And finally, we might be able to achieve more accurate solution on a quantum computer. So perhaps classical algorithms have to do some approximations, some heuristics, and with quantum computer, we'll be able to improve the accuracy of the solution. But more excitingly, quantum advantage may bring us new possibilities and to discover new phenomena that we wouldn't be able to probe using classical hardware, and to expand the frontier of our knowledge and to go on and improve research and so on. So for that, for pushing quantum experiments beyond what's possible using classical simulation, we want to do experiments with larger and larger quantum circuits, and one of the problems become the accumulating noise of the big quantum circuits. So in Qedma, we develop a suite for error mitigation solutions for quantum hardware, and this allows us to, I mean, if we stay with for example, if we stay with noisy quantum circuits, there is only so much we can do, and also much number of 2-qubit gates that we can achieve before noise takes over. But using error mitigation, we can push the size of the circuits and the number of 2-qubit gates further and further, and at some point even surpass classical methods and classical approximations, to achieve some kind of finite quantum advantage experiments. So this is true for noisy quantum computers, and also in the slightly further future, when error correction will take over. Also, error correction, while it's very efficient, it takes a very large qubit overhead, and so far we don't have, in the near future, we don't have this kind of very large overhead. So error mitigation will play a role even in the early fault tolerant regime, and so. In Qedma, we have the QSM software. QSM stands for Quantum Error Mitigation, Error Suppression Error Mitigation Software, and also QSM means magic in Hebrew. And this is a software that allows the user to interact with the quantum computer as if it was error-free. So the user indicates we provide the circuits and the observables that he wants to probe on the quantum computer, and the target position that he wants to achieve. And using hybrid experiments, classical quantum experiments with the quantum hardware, we do error mitigation. We apply several error mitigation techniques to reduce the noise and to mitigate the noisy, to provide extract back the answer without noise. And we do it with several innovations, so inside QSM, and it is also available either on the cloud in IBM Qiskit functions, so you can try it yourself if you want. And yeah, and for this project, we'll see how error mitigation improves and impacts the performance of quantum experiments, how it allows us to really push the boundaries of quantum, what's possible with quantum computation. So as everyone talked here, demonstration will do the Ising model, in this case, the Ising model on the IBM Boston computer. So we'll try to probe the magnetization in the 2D Torre Ising model on 51 qubits. So we can see the layout of the quantum computer, how the qubits are connected to the left, and they are in something that's called heavy hex connectivity, heavy hex geometry, and we have the parameters. So this is not just a transverse field Ising model, but it also have a longitudinal field of Z. So this is a Floquet Ising dynamics that uses both RVZ, Rx, and RV gates. And in this regime, at these kind of parameters, we can see that classical methods really start to struggle, and quantum computers can really push forward the limits of what's possible. So let's first look at some classical simulations at different sizes and see what's happening at bigger size. Right. So here are some classical simulations for smaller sizes, for 28 qubits and 35 qubits, and 35 qubits, right? And these are state vector simulations. So still, if you push forward, I mean, if you really load the cluster, a heavy cluster, and try to do state vector simulations for these kind of system sizes, it's still possible. And we can see the magnetization. So this is present the magnetization as the number of Trotter steps or Floquet cycles is the same thing. And we probe a later stage. You will see there is the initial state, and there is a later stage of pre-thermalization where the system still shows some magnetic oscillations before it's fully thermalized. And we can see that we have some oscillations at both system sizes, and their size shift a bit for 28 qubits to 35 qubits. So it's interesting how much we can push it. And I'll present here experiments done on 51 qubits. 51 qubits is already beyond the reach of classical computing, of exact classical simulations. And you will see what's going on. So if we go to 51 qubits, so here we present the classical simulations first. So there are two methods of approximate classical simulation. One is done with sparse Pauli paths. These simulations were done in collaboration with Blue Qubit and the Riken Research Institute, and it was done up to 700 billion of sparse Pauli path and above 500,000 core hours. So really, we put a lot of Riken and Blue Qubit put a lot of effort in trying to simulate these kinds. So these are presented in dashed lines, so for different number of sparse Pauli paths. And we also simulated some tensor networks, the same system by some tensor networks approximations using PEPS BP. So it's PEPS, it's two-dimensional tensor networks with belief propagation, some kind of approximate way to contract and simulate the dynamics. And also with few thousands of CPU runtime, we can see that up to about 12 steps, all simulations agree. And beyond the 12 steps, there is already a gap in simulations that are very hard to decide, and classical simulations have very hard time to converge and between those. So this is a gap that we can maybe try to do quantum experiments and to obtain new data that we couldn't obtain using the classical simulations. So here we present also the quantum simulations. So the unmitigated are in magnetization are in yellow, and the purple dots are the mitigated dots using QESM, and this is using the unbiased QESM mitigation. So the unbiased is based on PC, unbiased mitigation, and it assures that we have mathematically we cancel the bias, and it's not like zero noise extrapolation that there is some heuristic bias. Here we have a full we are sure that the error bars really present the statistical accuracy that we are looking at, and up to the error bar we have no further bias. And you can see also you can plot the z-scores of these mitigated values, and you can also see that the mitigated values go beyond the 12 cycles and already draw some fluctuations that are very hard to probe using classical simulations. So this already pushes the boundary, and there the question is whether we can do even better. So we introduced on top of this unbiased experiment, we we compared it to another heuristic error mitigation method, which we call the heuristic QSM error mitigation. And heuristic QSM can scale further for larger active volumes and exploits the error dilution, the effect of the error specifically on the observable that we measure, and therefore we can scale it even further for larger volume 2-qubit gates, and to go beyond what we can do with the unbiased QSM. And so you can see here before, I mean, how the noisy go on and on, and you can see on top of that, you can see that QSM heuristic performs quite, give us a more accurate prediction, and which is with agreement with the unbiased experiments that we obtain. And because their price we can allow ourselves to go further, we can continue and we can do more experiments in the for up to 30 Fouquet cycles, and really see some oscillations like in smaller sizes that we couldn't, although all these efforts we couldn't extract using classical simulations. And on top of that, we can also try to say, okay, this is heuristic. Perhaps we can validate these results using different quantum hardwares, and so we can present also mitigation on a continuum hardware. So you can see here the new points for the unmitigated results on quantinuum H2 and Helios quantum computers, and the mitigated values which are in great agreement on with the results from IBM, which is very nice because the noise model and the effect of noise on quantinuum is entirely different. So it's an entirely different story, and when both, I mean, the error mitigation for both computers reach the same conclusion, this really validates, I mean, the validity of the oscillation. And now, once we obtain the oscillation, and we can do some scientific work and ask, okay, how these sorry, I think it's later on, but we can really plot the magnitude of the oscillation as the size of system size, and see the trend and obtain some new insights about the physics behind this model. So here is some demonstration of the classical simulations, how they converge. This is for the sparse Pauli path. You can see that for millions and hundreds of millions, billions, tens of billions, still don't converge beyond the 12 steps. And this is for smaller sizes that we do have. So for this system size, we do have the exact state vector. So also for 0.5% of all the Pauli paths, so the 0.5% of all the memory that we have to take, this only done up to 12 steps. And if we want to do it even beyond that, here it is beyond that, sorry. So if we want to even push it beyond to a few teras of Paulis, I mean, still, I mean, just on about 50% of all Paulis at 21 qubits, were able to reproduce the exact oscillations here. So it's really hard classically to prove this kind of thing, and the quantum experiments really do a good job of extracting those. And I want to go back for a moment. I have the order of the slides here a bit confused. So here we can compare the different sizes, and we can draw some trends of how the oscillation, the magnitude of the oscillation scales with system size, and we can see that for infinite or for large and larger system sizes, there is some kind of a finite oscillation value that doesn't go to zero, which is a very nice conclusion that we don't have a very good theoretical understanding of. So this is some kind of free normalization of this system that it's really nice to see that we can probe exactly how it goes on using the classical, both classical and quantum data that we obtain. And This is not our only experiment that you can do with QSEM. You can use QSEM for many exciting different experiments. You can do it for, we have many different project collaborations of quantum simulations, of quantum phase estimation, so this is, for example, the first one is quantum phase estimation uses, again, the Ising model, and it is done in a variant which removes the ancilla without control qubits. So this is also a very exciting demonstration. And we have more collaborations with the University of Tokyo and with DESI. I think DESI is already published, and the University of Copenhagen as well. And with that, I'll finish. If you have any more questions, or if you like to read more or contact us, or maybe if you're interested to use QSEM for your quantum experiments and research, we'll be happy to collaborate and hear you. And with that, I would like to thank all the listeners.
Oh, thanks a lot, Matan. And it was a big pleasure to hear you. Now the discussion is open. So if everyone has a question, you can ask a question. There are questions in the auditorium. So I will ask with a question for all the speakers. So then you decide who is going to answer me. I read that our brain is a quantistic computer. So how do you have an idea how the brain reduces the noise? I have some personal interest in this. Who is going to answer?
Giovanna.
I would like to say that my brain is full of noise. I don't know about
Because I have some personal issues on this.
But I don't know how. So the idea of the quantum computer as the brain working like a quantum computer is something that is being brought forward by Roger Penrose, and there is a chapter in his book, The Emperor New Mind, in which he was discussing strong AI, which is becoming now very important, and the fact that the brain is completely different, doesn't work algorithmically like AI things. Now, this is not something that I think one can prove, or at least one can prove it, but at the moment we don't have something, the equivalent of the Bell inequality in order to quantify an hypothesis with respect to another. But what I would like to say is that living organisms use noise in order to enhance a response over another. So there are several examples of biological systems that are also modeled by algorithms in computers in order to shape and optimize classical dynamics. So living organisms use nonlinearity and noise together in order to amplify a response over others, and they do it in a very efficient way. Quantum systems, we don't know, but I find it a very interesting question. Thank you.
Thanks to you. Emanuele, there was a message that someone is muted, so cannot.
Oh, yes. Sorry. That's right. My mistake. Yes. Okay, yes. Now everyone can unmute itself and ask questions. Sorry.
So thank you, Emanuele. The next question, please.
Sono ancora chiusi, eh? Non sono aperti.
Adesso sono aperti. He can ask.
Yeah, I have a question regarding the cancellation of noise that was presented by Professor Morigi. Is this for an ensemble of qubits, or is it for a single qubit? Because my experience with qubits is that each qubit has its own history and its own noise that it feels from its own environment. So cancelling the noise of an individual object is very different than cancellation of noise from an ensemble of qubits. Can you comment on this, please?
Yes, so first of all, I'm happy to meet Eli Barkai, even so virtually, the first time, so nice to see you. Indeed, a fundamental ingredient of the protocol I was discussing was a spatial correlation of the noise. So this means that the fluctuation at every qubit is correlated. Okay, this was important. And this means that the type of protection I was discussing could be achieved, say, if there is a global coupling to some sort of environment, or say if the qubits are within a region where the fluctuations of the environment can be assumed to be correlated over the ensemble. If the qubit feel each on a spatially decorrelated noise, this in this case would be modeled by individual environment, and what I was discussing cannot be applied.
Okay, thank you.
Mm.
I can ask many questions if you want.
Maybe we can meet if you want.
Please go ahead.
I had a question for the last talk for Matan. I mean, what do we learn about the noise in this system? What is the origin? Is it dephasing noise? Is it decay noise? Or is it everything? And can your company help us define the noise?
Right. This is a good question. In IBM superconducting quantum computers, I mean, you can ask two questions. You can ask what is the underlying fundamental noise model, like the dephasing and decoherence, amplitude damping. You can characterize the different components of that, and for error mitigation. So I mean, there's also our error mitigation is done using characterization of the underlying model. So QSM first have a first characterization model that characterizes the noise of the quantum computer, and then it characterizes also some over rotation. It calibrates the rotations of the quantum computer, and then it applies some mitigated circuits based on this noise model. So there is the base model, which is, I mean, it's based on the kind of things that you talked about. And also there is a level that we do also some kind of noise averaging. So there are certain methods like twirling in which you can average a noise model of all the phasing and amplitude damping. You can average them together to obtain some kind of more uniform kind, either a local decoherence, a 2-qubit decoherence model, or some general Pauli channel. So you can, using some smart compilations, you can reshape the effective noise model, which enables us to perform more robust error mitigation. I mean, we have a team that does noise characterization. I'm less familiar with these specific aspects and details, but I can point you to the right researchers if you like.
But is it provided, namely, when I go to the doctor, I want to know what is the prognosis and what is the medicine. So you give me the medicine, this I understood from the talk, but do you give me also some more information on the noise, or you do not do that? As a company, I'm asking.
Yeah, in our product, I don't think we give, I think we give a average infidelity value, and the noisy value and the mitigated. So we don't give a full profile of the noise to the user.
Okay, thank you.
So there is
a question by Paolo. Emanuele.
Yes, but Paolo was asking, there is a question from Paolo Barbanti. He asked if there are applications of quantum computer to the folding of complex protein molecules, DNA modeling, and drug discovery. I know that there is AlphaFold, but you are the most expert in the field, so you can answer.
I don't know, Emanuele, you want to answer?
Matan, I think actually in your slide, I think you had an application for the world of chemistry. So maybe you can show again the slide and comment on it. I think it on the one hand it shows the opportunity, but also the challenge.
Let me see what I have.
I think it's something, there was a molecule of water, if I remember correctly.
Yeah, so in quantum, just a moment.
Voila. Okay.
Right, so in quantum chemistry here, Yeah, so the VQE, so in quantum chemistry, one of the targets of doing quantum chemistry on the quantum computer is to scale for scaling for larger molecules and achieve a chemical accuracy. There is some criteria for chemical accuracy in which, I mean, it is useful. The ground state and the energies are useful for chemical reactions. So currently, most demonstrations are for a relatively small scale, and people are trying to push the boundaries for larger systems, large embedded Hamiltonians of molecules, and there are many different approaches to how to extract the ground state energy. There's some. So here is a demonstration of, I think, a VQE, and you can see how the energy changes with the bond's length up to a good accuracy. But you may have there are some other works by IBM, I think, and
yes, IBM, I know.
about kind of doing some sparse diagonalization. So sparse sampling of the quantum computer in order to do a subspace diagonalization of the Hamiltonian. This is called the SQD, and there are many variants for that, and there are people in IBM and RIKEN that push it forward. And again, I'm not an expert for quantum chemistry, but this is what I can comment on.
Can I ask
other
a
question
question
from the
to
audience?
Matan? So can you go to the last slide, Matan? So what
Okay.
is, I'm focusing now on the purple dots. So the purple dots is, if I remember correctly, or maybe the blue, I mean, this sort of violet. Yeah, the purple. So in the purple dot, it's, you basically stop after 15 cycles. This is the unbiased estimator. Now, what happens if you go further? I mean, should I expect the error bars to increase dramatically, or what happens? Why did you stop there?
Yeah, it's mainly a question of accumulating statistical knowledge. So error mitigation has quite difficulty in general to scale to larger and larger systems because you have to pay a price. So the price of the heuristic, the unbiased case and mitigation is similar to the PEC method, in which you have to the overhead of mitigation grows exponentially with system size. Exponentially with the volume of the quantum computer, the number of 2-qubit gates. So you have to reach some point and put many compute resources and QPU time. So a few hours QPU time at which point is it? Is 14 steps or something like that. And from then onwards, it's just too expensive to continue because you have to gather lots of statistics using many experiments. So this is why, I mean, the heuristic error mitigation is slightly different kind of scaling, and it allows us to probe a little bit further and to reach more deeper circuits. Yeah, but that the unbiased mitigation has difficulty to arrive.
Yeah, thanks. This is useful. I actually have a comment. Maybe, but it's also maybe a question for the other speakers. So, Matan, in your presentation, you began by saying, okay, in what sense the quantum computer is better? So maybe it is because it is faster, maybe it is more precise. I think there is also another parameter that now people are talking about, which is energy consumption. Right? Because in terms of the classical computer, you can always say, well, you use 1,000 GPUs, fine, buy 2,000 GPUs. So in a sense, I mean, what is the velocity of a single GPU meaning when you can just buy more GPUs? But then something that also needs to be taken into account is how much energy you spend. So yeah, I mean, I was at the conference actually in Italy last month, and the CEO of D-Wave was talking, and he was saying, well, the quantum computer can be more energy efficient. And at the beginning, I thought like it was, I don't know, nonsense. But then when I thought about it again, I said, well, actually, I don't know. I mean, Matan, you showed the simulation on, thousands of hours of CPUs. So I mean, this has some cost in terms of the energy. I mean, for 500,000 hours of CPUs. I mean, there is some energy that goes there. So I don't know, maybe it's something that needs to be taken into account also. How much energy, like just the electric energy you need to use in order to run those GPUs.
It's not easy to evaluate. I mean, the cryogenic apparatus of a D-wave machine needs energy, right? So
I don't know. I mean, I think that the IBM dilution fridge is, I mean, just not. It's not a terrible machine. I mean, I'm not really an expert, but I don't think sure, it consumes energy, but it's not. I mean, you don't need a small energy. We certainly have dilution fridges at Bar-Ilan, and we don't have an energy.
I think it's not easy to. I mean, the point is that you cannot set a bound like a Landauer bound for energy consumption, and decide on that basis, right? So it's not. I don't think it's that straightforward to evaluate. So.
No, but I mean, it's a real question. I mean, you can ask, okay, how much energy did you use to run your dilution fridge, and how much energy did you use to run 500,000 hours of CPU?
We can compute the work statistics of a quantum computer. That can be done. Can I ask a question to Matan? I'm not really an expert of what you're doing, but I just wanted to ask. I remember from the IBM paper that they use zero noise extrapolation, and well, then there is some other technique they mentioned, but they're not using it to mitigate errors in their experiment. So in that respect, how much better your machinery would be in comparison, for example, to zero noise extrapolation and techniques of this type?
Right, that's a very good question. I'm sorry I don't have a slide. We have a prepared slide for that. Okay, I don't have the citations here, but if you look at papers by Qedma, there is a full report about the error mitigation techniques used in QESM, and you can see there is a demonstration of the difference between different zero noise extrapolations and other error mitigation techniques and our product. I mean, zero noise extrapolation is many times very useful because the overhead of doing it is not very large. You can achieve some nice extrapolation of a reduction of the bias without much effort. But this is also, there is a price to pay, which, I mean, there is some bias, some residual bias that is very, very hard to characterize. I mean, it depends on the method. There's methods that are more robust against that. There are most of the methods that are less. But our product is basically the QESM mitigation is primarily based on a probabilistic error cancellation, which tries to cancel the error mitigation by some QB decomposition, doing some QP decomposition of the noise model and its effect on the observable, and canceling these effect by reducing by counterbalancing the contribution of errors. I mean, just summing over some mitigation, the expectation value, some over mitigation circuits. So we have a demonstration in our paper that shows in the case of transverse field Ising model, once again, it shows the discrepancy between several zero noise extrapolation methods and our mitigation result. Basically because we are basing our results on PCN characterization, we can provide guarantee that the actual retrieve value is within the target within the target precision. So this is one feature that is in our QESM, in our product, that is better than usual ZNE. But I make you look at the paper, and there is a very detailed.
Thank you.
Sure.
So we have a question on chat for all the speakers, and the question is, I will a bit summarize. How can quantum computing be used in material science? I've heard about its use in crystallography and material discovery, but I couldn't understand how. If someone from the audience can answer, we appreciate.
Yeah, I think maybe I can address this question. So think of, imagine of the following question: how to build a material that is a superconductor. So this very simple question is actually unknown a priori. So if you give me a material which is formed by certain atoms, so you decide which atoms you are going to use for your material, and provided you can synthesize this material, will it be a superconductor, let's say at very cold temperatures or not? And it is an open question. I mean, we know from the experiments that some materials are superconducting, and we roughly understand why they're superconducting, but it's really hard a priori to answer this question without first measuring the material itself. So a posteriori, we justify, say, oh yes, this is a superconductor because so and so, but a priori, predicting the superconductivity for complicated materials like layered materials it's an open question. And in principle, the quantum, how does the material know if it is superconductor or not? And the answer is, well, the electrons that are in the material, they look for their ground state, let's say if you cool it down, and depending whether the ground state has this so-called long-range coherence or not, it will be either a normal material, an insulator, or a superconductor. So it means that the question of whether a material is superconducting or not is a question of quantum mechanics. In principle, if you had a very powerful quantum computer, you would be able to address this question and to solve, to sort of model the problem on the quantum computer. The quantum computer will be able to solve and tell you, yes, this material is going to be a superconductor, and let's say what are the critical temperatures, is the critical temperature of the material or not. Which means that instead of going to the lab and building that material, you can ask the question theoretically on the quantum computer, and ideally, if you can do it fast, you can maybe check many materials until you find the material that has the property, say, superconducting, but it could be also another property that you are interested in. So because a material it's really the properties of a material, it's really depends on the behavior of the electrons, which is a quantum problem. So the quantum computer can predict the behavior of material, and in that sense could be useful for material sciences. Now, I use all these conditionals, could, maybe, etc. And the reason is that you wouldn't, for a complicated material, it's not usually a single electron problem, it's a many electron problem. Usually in the results of tens or thousands of electrons, you need to simulate or mimic using a quantum computer, which is far beyond the current capabilities we have. So yes, in principle, that's how it could be done, but in reality, this is really still a bit far away. In crystallography, I'm not really sure how this is relevant. I saw also Giovanna raise her hand. But before I give the microphone to Giovanna, I asked the chat actually. I asked this question. So how much electricity? Well, I can share my screen. So we have one more speaker here, which is ChatGPT, that can now contribute to our presentation. So this is the question I asked. Assuming you have 500,000 GPUs, so how much energy does a dilution fridge of a quantum computer for 10 hours versus 500,000 hours of classical CPUs on a high performance computer? And the answer that ChatGPT gave, and it will be interesting to check whether this is correct or not, is that actually the Matan's high performance computing consumed 30 times more electricity than the quantum computer. So I don't know if this data is correct or not, but actually it's an interesting way to compare. Instead of comparing hours, to compare because again, hours you could just take a larger high performance computer, but comparing how much electricity you're using to simulate that problem. It's an interesting twist, actually.
Did you ask how much money does it cost to cool down the helium?
Well, next, I'll ask her offline and report. Thanks for the question. Who was it, Odette?
Yes.
Okay, but I think
after all, I'm in chemistry. So.
Yeah, thanks for that.
This is also like the fusion result, the laser confinement fusion, where they get out more energy than they put in, but not if they count the amount of energy it takes to operate the lasers, right?
Any other question?
I saw
Comment?
in chat one student from India that want to ask
I
something.
just asked Christina.
Yeah, we addressed. Giovanna, did you have anything to say?
Yes, I was very, I think the point you made on energy consumption is very important. And the point that Alessandro touched upon, that we have way to calculate the world statistics, is an important step ahead, but it's not sufficient because it is based on we have this ideal dynamics, then we know how to calculate the world statistics. When we don't know how to connect the resources we need. And the question you asked to a computer, to a robot, say, is a starting point to make this assessment. And I would say this is a very central question for the development for the field.
Any other question? So I think the discussion was already quite long. So I want to thank all the speakers for the wonderful presentation. I want to thank a lot IC for the organization of this webinar. And now, for the closing remark, I give the stage to Professor Cristina Bettin, that will tell us some few words of closure of this.
Thank you very much. First of all, I would like to express my sincere thanks to our distinguished guest. Really was an outstanding presentation, and I was able to understand that I come, from humanities and social science. It was very, very interesting, very fascinating. Thanks a lot to Professor Farini for his collaboration and his commitment to strengthen, this partnership between the Italian Embassy and the EC. And to all the participants, of course. And we're looking forward to continue with our collaboration with the Italian Embassy through several academic initiatives that will further strengthen, the dialogue, the scientific and cultural dialogue between Italian and Israeli researchers, wherever they are, like Giovanna that is in Germany. So thank you very much. So I want to spend just one word to say that our next initiative, together with the Italian Embassy, will be the Italian Research Day in the World. It will be a huge conference, and we plan it, for November or December, and so we hope that you will enjoy us then. And we don't know yet exactly the location, but might be, in one of our university, perhaps in the Weizmann Institute. And you will be informed about the date. And then, will be presented several panels, not only in physics and chemics or in different science, and also some kind of humanities and social science. And we will give also room to our young researchers, like a PhD and postdoc, to present their posters on the last research that they do about it. So you're welcome there. And thanks again a lot. Thank you. And Giuseppe, if you want to say something else to close, but
Thank all you on behalf of the ambassador for participating to these events. We really appreciate your commitment, and we thank all you once again.
Thank you very much to all of you.
That Emanuele is still working.
Yeah.
Emanuele is still working on the chat. Emanuele, if you want to comment some things, you are.
Yes. No, I was saying that I asked about the helium, and the chat still maintains it that the QPU wins, but I don't know if it is correct or not.
Thanks so much. I really appreciate your attitude. Well, thanks.
Thank you.
Thanks, all.
Thank you.
Bye.
Thank you. Bye-bye. Thank you a lot. Bye-bye.
Bye.
Bye. Thank you.